suppose you want to make a movie. For example, maybe you want to tell someone you love them. Or maybe you want to empower the world with instructional videos on math and science. Or maybe you want to help people understand their feelings with a movie about joy and sadness. But whatever it is that you want to convey in this movie, what you probably don't want people thinking is, why does it take so long to download? Right? That's the most annoying thing on the internet, is waiting for movies to buffer. That said, the people who make movies spend a lot of time at it. They labor over it for months or years. And so they pay attention to every frame and every pixel of every frame. And they want to make sure that the audience sees the movie exactly as they intended. So this leads to a question. If you have Wi-Fi at your house, and maybe you want to stream a movie, is Wi-Fi fast enough to stream every single pixel exactly the way the director wanted you to see the movie?
No.
Well, right. The answer to this question is, in fact, no. And let's do the math. Let's think, what is a movie, right? To a computer, a movie is nothing but a sequence of colors that flash and change over a period of about 2 hours. So every movie is a bunch of frames, and each frame is a bunch of pixels. Each pixel has an amount of red, of green, of blue. And so let's just add up how many bytes is a movie. So a movie should be about this many bytes. So if you have a high definition movie by the 1080p standard, then that means you have 1920 pixels wide by 1080 pixels tall. Okay, so that's per frame, how many pixels, times 3, that's the number of colors, red, green, and blue. So that's the number of bytes per frame. Now a standard Hollywood movie has about 22 or 24 frames per second. So multiplied by 24, they're about 60 seconds per minute, 60 minutes per hour, and about 2 hours. And so this, if you multiply it all together, a standard 2-hour high-definition movie takes 10 to the 12th bytes. Now this is a lot of bytes. This is called a terabyte. So a terabyte is 1,000 gigabytes, which is 1,000,000 megabytes. Right? My laptop here, brand new laptop from Apple, has a hard disk that's 250 gigabytes. It could not store this movie. Right? This movie is very, very big. But let's think, we want to stream this movie. So we have a lot of time. We have 2 hours to stream the movie. So let's see, how fast is Wi-Fi? So if you're on a good day, and you're using the modern Wi-Fi standard, and you're not splitting the Wi-Fi with your brother or your sister or your parents, then that will download at about 10 megabytes per second. So that's 10 to the 7th bytes per second. That's the maximum Wi-Fi speed. Yeah.
Isn't it 100 megabytes per second, or is that for Ethernet?
That would be more like for Ethernet, but I think this is the 802.11g standard for Wi-Fi. But nonetheless, the point is the same, even if we give this an extra factor of 10. Okay. So if you do the division, you say, how long does it take to download your 2-hour movie? It'll take 10 to the 5th seconds. That is about a day. So this is a seeming contradiction. On one hand, it should take a day to stream a 2-hour movie, yet we do it all the time. So I actually want to show you another contradiction that's a little more mathematical in nature. So I wanted to show you that, in fact, most movies cannot even be put on a DVD. And we can do this simply by counting. So this is something that mathematicians will call information theory. You just count the number of things that are possible. So let's count how many possible movies are there in the universe. So, well, we've already said a movie is about 10 to the 12th bytes. Right? What is a byte? A byte is 8 bits. Each bit represents on or off, so 2 choices. So 2 to the 8th is 256 choices. So the number of movies that exist that could ever possibly be made is 256 raised to the 10 to the 12th. So this is some number. It's a very large number. Okay. So let's think about a DVD. How big is a DVD? It's about 5 gigabytes or so. And I mean, there are better ones that are out there, there are Blu-rays, but anyway, on the order of about 5 gigabytes. So that's about 10 to the 10th bytes. So the number of distinct things that you can put onto a DVD is 256 to the 10 to the 10th, which is that. So we can see that these numbers are both very large, and that the number of movies is much larger than the number of things you could possibly put on a DVD. And just to give some perspective of these numbers, let's think how many atoms and how many molecules are in the universe. So according to some studies, it's around 10 to the 80th or 10 to the 85th. Right? This is like 10 to the 10 to the 10th. Right? These numbers are beyond astronomical. Like even the numbers that you come up in astronomy don't hold a candle to these numbers. Right? They are that big. Right? But the point here is not so much that these numbers are really big, but that there are many more movies that one could have than things that you can distinguish on a DVD. And so there's now a fundamental mathematical problem about putting movies on DVDs. And it's something called the pigeonhole principle. And that principle is as follows. Suppose I have 100 pigeons, and I have 10 holes. And I have to put every pigeon in a hole. Then what I know for sure is that some hole has multiple pigeons in it, right? Simply by counting. Right? But not only that, I know that most pigeons have other pigeons in that same hole. Right? There are 100 pigeons in 10 holes. Most of them are going to share one of the holes. Right? So this is the same thing. The pigeons are the movies. The holes are the bit sequences on the DVD. So no matter how clever you are at saving your movie in a really original way that saves space and is very efficient, you're going to have collisions. There are going to be most movies will share a sequence of bits that is the same as the sequence of bits for some other movie, hence you can't tell these movies apart. Right? This is a fundamental mathematical problem. So we've seen two contradictions. Right? One is that we shouldn't be able to stream movies exactly in real time. And the other is that most movies we can't put on DVDs. So what is the resolution? Because after all, we do this every day. We watch movies every day. And the resolution to this is that most movies are boring. And that that's very important. So when I say most movies are boring, I'm of course not just talking about Die Hard 17, which may be quite indistinguishable from all of its prequels. I'm talking about movies that are even more boring than that. Now, if I'm going to say that most movies are boring, I'm actually going to hold this claim to a very high standard. What would it mean to make this claim? Right? I'm going to say most of this object have this property. Let's say I wanted to know if most Americans believe in mathematics. Well, what would I do?
Take a survey.
You would take a survey. And what's the best, if you were to design a good survey, what would that survey do? To who? Ask questions to who? So to everyone in the country? You have to take a random sample. Right? So you would take a random person, you'd ask him or her, do you believe in math? And then if you do enough of those, let's say you take 1,000 of them, and enough of those people say yes, then we can say most Americans believe in math. So it's the same thing here. If we want to know, are most movies boring? Let's take a random movie. Let's survey over the set of all movies. So now this leads to a question. What does a random movie look like? What does a typical movie look like? And now we have to think back to, well, what was a movie? It was a sequence of pictures, and a picture is a set of pixels, and a pixel is an amount of colors, and each color has a value between 0 and 255, 1 byte. Okay? So if I choose random values of all of those, and we plot this, the frame of a typical movie will look like this. It will look like static. Has absolutely no structure that is at all interesting. I mean, imagine trying to look at this for 2 hours. I think we could all agree that would be very, very boring. Now this is, of course, just one frame, but if I were to generate frames of this all day, every day, since the dawn of time, they would all look like this. Even though I'm just as likely to choose this frame as the frame from any Hollywood movie ever produced. And this is an important thing. It's saying that most movies, most images look like static. So that means that most movies are boring. So this is now an opportunity in disguise. The fact that most movies are boring is telling us something. It's telling us that the information in the movie is not all that necessary. Right? If we have a terabyte of data, and all that that data is doing is distinguishing this pattern of static from that pattern of static, then, I mean, we can't even see the difference. So that information isn't visually discernible. So if information isn't even discernible to your eye, that creates 2 opportunities which I want to discuss. So the first is if the information isn't useful, then you can use it to hide secret information into your images. This is something called steganography. The second thing I want to show you is that if the information isn't useful, then don't store it. Okay? So these are 2 very interesting ways of using this important fact. The fact that most of the information in a movie, your eye can't even tell apart. Okay? So let's talk about steganography. Steganography is the art of hiding information in signals, so in movies, sound files, images, hiding that information in a way that you can't even see that it's there. And let me show you how that's possible. Here's a picture. It's kind of boring photo, but it's kind of pretty. It's a 5x5 grid that goes from kind of grayish to white. Yeah. It looks totally benign. If you were to see this on the internet, you'd be like, why is that there? I don't know. And then the numbers on the right are the shade of gray of every one of those 5x5 pixels. Right? So 255, that means white. Right? And so the lower right-hand block, the lower right-hand pixel is white. Then the upper left-hand pixel is 97, so it's closer to black, or some sort of shade of gray, and everything is in between. So now I'm going to tell you I embedded a secret message into this data. If I didn't tell you how I did it, you'd be like, I don't know. But I'll show you how I did it. What I did is I just changed the last digit to either be even or odd in accordance with my message. So here we notice some of those are even, some of those are odd. So let's highlight the odd ones. And there it has a secret message that says, hi. Normally the I is a little smaller than the H, but it's hard in 5x5 to get it to be typographically ideal. So this is using an important fact, right? Your eye cannot tell the difference between shade of gray 97 and shade of gray 96, right? We've just chosen enough gray shades that we just barely cannot tell the difference between them. And that's what allows us to store this data. Now you could think, well, is this actually useful? And the answer to that is yes. The industry uses it all the time. Like let's say you're Hollywood, and you have a bunch of people to give, who are going to rate movies for the Oscars. And you're going to give them a digital copy of the movie. Right? This is kind of a perilous proposition because things can leak. Those movies can somehow appear on the internet. And then who are you going to blame? Well, who? You gave it out to hundreds of people. So if you could embed secret information into the video, such that you could play the video and not even notice it, you can embed the information of who you gave the video to. And then you would know that, who it was. So this is actually not a subliminal message. So a subliminal message is something your eye actually sees, and if you paused it, you would see that message. This is something that's in the low order bits, the differences in color that no one can even notice. But if a computer goes and looks at it, it will know that that they're there. Right? So this is very different. So this, of course, you can envision other applications. The music industry can do things like this. And they're very, very clever ways of hiding information in data. So this way is not actually that good of a method. Let's think, why is this not a good method? Well, it comes to a principle of encryption, a principle of security. And that principle is your system should be secure even if people know how you hid the data. Right? So there's another competing description of security, which is called security through obscurity, which is don't tell people how you hid the data and they won't find it. And that doesn't work. Right? Because someone somewhere is going to be smart enough to figure out how you hid the data. Someone's going to look at that and be like, maybe just they're playing with it and looked at the last bit in the data and they know, oh, this is odd, the last bit's crazy. And then they see, oh, it's a message, and now they can change the message to say whatever they want. This is a very dangerous scheme for hiding information. But nonetheless, it illustrates the point. And there are much more clever, much more interesting, much more difficult to attack ways of hiding information in data. So that's steganography. That was our first main application of the fact that most data isn't visually noticeable. So, but we have an even bigger point, which was that if most data isn't noticeable, then why store it? And this leads to a central question in signal processing, which is how do you make more with less? How do we use less data to recover a signal? Because this is, after all, the central question. I want less time to stream. I want to take fewer pictures. I want a cheaper, mission to Mars. All of these things. We want to make more with less. So how do we recover a movie or a picture with less data than the true size of that signal? Right, so that's the term we use. We say compression. But how does compression work? That's where we're going. But before we think about compression and how compression works, let's think about this statement. This actually contradicts something that you've been told for years in algebra class. Right? What you've probably been told is, if you have two unknowns, well, how many equations do you need? You need 2. If you have 10 unknowns, you need 10 equations. N unknowns, N equations. Well, a movie has 10 to the 12th unknowns. So if you're going to tell your algebra teacher, well, I need 10 to the 12th equations. Each equation is an amount of data. I need 10 to the 12th data. Now we're back to our original contradiction. So this is a very surprising question. The fact that we don't need all the data is incredibly surprising. But there's still, so we haven't answered this question yet. So we said we need to compress. But what's the idea on which compression is based? That is the idea of structure. You make do with less data by understanding the structure of your signal. Most signals look like static. They have no structure, which is to say you can't compress them. There's nothing you can do. There are just too many near-identical signals. But most movies, most videos that you want to take in the real world have structure. And if you can identify that structure, then you can store that movie or that image or that sound file with less data. So let's talk actually about 3 applications of this that are all very, very cool. And let's start with JPEGs. Right? How you've used JPEGs all of your lives, probably without even knowing it. And what's interesting about JPEGs is they're a type of image that only works for a type of picture. Right? They're GIFs, they're PNGs, they're JPEGs. So does anyone know what type of image is a JPEG best for? Is there?
A really large image?
Okay, well.
Because isn't it a compression algorithm? When it stores it, it compresses the image?
It's true, but there are large images that's like a billboard that you're putting on the wall that's, a logo of a company. And then there's large images of, cats, and I mean, of lots of things. So actually, the size of the image isn't really the special thing about JPEGs. Yes. So the comment was maybe they're better for small devices like phones, and this is close. This is close because what do we do with phones? What do we do with phones and images? Well, we take pictures. And what do we take pictures of? The world. In particular, we don't take pictures of static, usually. So a JPEG is a type of image that is best for naturally occurring photographs. It's not good for logos. It's not good for, certain types of, unnatural images. So now we have to ask, what is the structure of a natural image? Well, let's give ourselves something that you might, take a photo of. Let's look at this object. This is 3 Reese's peanut butter cups being shot at by a 22mm rifle in the MIT Edgerton lab. This lab is famous for high precision photography. So based on the sound of the gun, there's a sensor, it knows how far from the gun to the object it is, and so it times the photo exactly right. And there are very famous photos that come from this lab. You may have seen one with an apple and a bullet going through it, and you see the whole thing. Right? So this is a natural image. It's something we took with a camera. So one of the ideas of a JPEG is to break it up into 8x8 chunks. And let's look at those chunks. So let's zoom in to one of those chunks. I just chose one. That 8x8 square looks like that. So we notice that it does not look like static. Right? It has this structure. It's kind of constant along horizontal lines in this particular square, but it has this kind of like smooth gradient. It starts at white and ends at this orangish brown. And so we see there's this property that natural images are smooth. There's a little bit of variation between pixel to pixel, but most images are smooth. And that's the property that we want to capture. So how do we do that? Well, we actually use some very sophisticated mathematics, which we can show in a picture. And here, this is one of the most important mathematical properties to have ever been invented, is the following idea. That any 8x8 block that you can imagine is the sum of these blocks. So this is an 8x8 array of squares that are all 8x8 pixels. Right? So I have 64 canonical images in some sense. And I can add them together, subtract them, multiply them by constants, and then I can form any image I want by a combination of these. So this is actually not that surprising. After all, an 8x8 block has 64 pixels, right? So there's 64 unknowns. So there's 64 things here, so that's 64 equations. And so I express 64 unknowns and 64 equations. And so that's expected. So that's not what's special about these blocks. But we can look at these blocks. They have structure. Right? If we look at the top left one, it's a constant. That's the smoothest thing you can imagine. Right? If you look at the one to its right, it starts at white, and then it goes to black. So it's just a gradient. Okay? And so that is less smooth than the constant, but still pretty smooth. And then the one below it is a gradient in y. And then if we keep going over, so the 1, 2 position, it oscillates twice. It goes from high to low to high. And the fourth on the top, it goes from high to low to high to low. So it's the number of times it oscillates is the column that it's in. And actually, if we want to write down the formula for these, this is fairly simple. These are like cosine of nx times cosine of my. Okay? So you'll remember that cosine is just a function that oscillates from high to low. So these fundamental blocks are just the product of an oscillation in x and an oscillation in y. And if you have all of them, then you can express any image as a sum of these. So you already know the tools to understand these images. Right? So now let's go back to natural images. Right? We said that they're smooth. We said if you take an 8x8 block, it looks more like what's in the top left than what's in the bottom right. So that means you only have to store how much of the blocks in the top left are there, and not how much of the blocks in the bottom right. And so if you don't have to store the data in the bottom right, now you've compressed. You've gotten rid of data, it takes less space. So this is JPEG compression. So let's see this on a real image. This is a photo of a cat. But what's special about this photo is that on the right, it's very high definition. It is a high quality JPEG. It has a lot of those blocks. On the left, it's the lowest quality JPEG imaginable. Every block only is allowed one thing. And so you can actually see the blocks. Right? So let's see. Let's zoom into this picture. Let's zoom in somewhere in between, like halfway point. It looks reasonable. It takes up less space. It looks like a cat. So let's zoom in and see what those pixels look like. Right? So we zoom into the nose of this cat. We see that, in fact, each of these blocks looks like those blocks from the prior slide. Right? Let's look at this. This is just a gradient in x. Right? This is also one of the blocks. Up there is a flip-flop pattern, which is also one of the blocks. So we see that in JPEG images, we've actually used very few of the blocks to describe each 8x8 patch in the image, and that is how we got away with less data. Now that came at a cost, though. Right? The cost was that we've changed the image. Right? Those exact pixels on the nose of this cat don't look exactly like that. Right? We've thrown away some of the data. And in many cases, this is fine. For natural images, photos of people and cats, we're fine with losing some of the quality of the images. But there are some cases where we are not okay with losing quality of the images. So this would be the second example. A very recent example of something where we will not tolerate loss of quality is an image like the following. This is a picture of Pluto, taken by the New Horizons spacecraft about a week ago. This is a case where we will not tolerate errors in the image. After all, if we're going to spend $700 million and over a decade of effort in design, development, and transportation of this satellite to Pluto, when we get back an image, we want to know, is that a mountain range or is that a JPEG artifact? Right? That's not an acceptable question. Right? We, in this case, will not tolerate loss of, sort of errors in the image. But now we're back in our conundrum. Images are big. Data transmission, especially from Pluto, is not very fast. In fact, does anyone know how many bits per second we can communicate with this spacecraft from Pluto? Any guesses? 1 bit per second? Or you can do a little better than that. The answer is 1,000 bits per second, or 125 bytes per second. But you probably never even thought about bytes per second with numbers that low. Right? But 125 bytes per second. An image is 1,000 by 1,000 pixels. Each pixel is, let's say, 12 bits. So that's 12 million bits that we need to send. That's a lot of time over that signal. Plus, you have to remember there are other sensors on the spacecraft. Right? There are other things that we want to communicate back and forth with. Plus, we need satellite dishes on Earth to receive these signals. Those satellite dishes are only in the right direction some of the time. Plus, other people want to use those dishes to do other things. Right? So now we have a problem. How do we send these signals using less data when we won't tolerate any data loss. And so there actually is a way of doing this, something called lossless compression. And now I hope right now you immediately said, well, what about the pigeonhole principle? Right? Lossless compression. I have a bunch of things this big. I make them take this much space. But now some things will collide. I will not be able to extract it because certain signals will take up the same amount of, the exact same space. And so we're back to our central problem. Is that how do we get around the pigeonhole principle? And again, the answer is you use the structure of the image, right? This spacecraft is not taking a picture of static. If it were to do so, this would be a hopeless task. It's taking a picture of a rock in space. And what is happening in most of this image? Is there
A lot of white.
Yeah, but that's the interesting part. That's the part we don't want to throw away. We have a lot of black. We have a lot of space that is very much not interesting. So lossless compression capitalizes on the structure. The structure here is there's a region of interest surrounded by a sea of black. And there are other things you can do too, but that's one of the ways of storing this data in less space. And so in fact, instead of having to send 12 megabits of data, they actually only have to send about 2.5 megabits of data once you get rid of all the black and other things. So that's an incredible savings. So this was our second example of how we can get away with using less data. So our final example is also very interesting. So, but let's think abstractly a little bit. If we need less data to store images, then this gives us an opportunity. But let's think again. We have normally a camera which takes a picture, which that is to say, in every pixel it records how much red, blue, and green is there. It gets all that data, and then it's going to save it as a JPEG, and it's going to throw away most of that data, and then we're going to see the JPEG. Right? This seems kind of wasteful. After all, if we only want this much data, why collect this much? So there's this new paradigm in imaging, which is to just collect less data to begin with. And this paradigm is very relevant in medical imaging. For example, with magnetic resonance imaging, or MRI. So I don't know if you've been in an MRI machine, but I have. At one point I had a cardiac MRI because I donated a picture of my heart to an academic study so they could have a three-dimensional model of a heart. And the experience was traumatizing, to be completely honest. Like I went into the NYU Medical Center. There's this dark room with this big machine in it. I sit on this flat bed. And then the bed takes me into this tube, which is about this big in size. The doctor says, don't open your eyes, you'll get claustrophobic. Right? So now I'm hearing the gears turn as I'm going into this tube. I close my eyes. So literally this is what I'm seeing. And so then we're going to take an MRI of my heart. So the thing about MRIs is that they take a long time. And that's just a mechanical thing. They send waves through your body. Then mechanical pieces have to move. They send different waves through your body. And then through all of the detectors, they can then figure out what the picture is of the tissue inside of you. Okay? So, but of course, as you know, with pictures, you can't move, or else they would be blurry. So now, I have to sit there for 20 seconds and not move. But remember, this is a photograph of my heart. And that creates a problem, which is that it's involuntary muscle. Not only that, it's attached to my lungs, which I also need. And so there's a trick to do this. You hold your breath for 20 seconds. Okay, that still doesn't stop the heart from beating. But then what they do is they follow your heartbeat, and at every point of the heart cycle, exactly the same point, they then take another measurement. And they do this, and so it takes like 20 seconds of breath hold, and they get a bunch of data. And so then I was in this machine for an hour and a half. That was a long time. And I remember, all that happened in that time was the doctor saying, breath hold 20 seconds. I'm just like, okay. And it was tough. So about an hour and a half in, I was just like, hello? Is anyone there? And no one replied. And then I started freaking out, because I'm like, maybe the doctor just went on a break or something. And so then the doctor's like, calm down, I'm here, your heart's beating too fast, we need to pull you out. Right? So you can see that this is a real thing. Using less data to take images is very real. It has a strong effect on, the very least, how comfortable it is for people to get MRIs. But that's just small potatoes. Really, there's also a matter of life and death involved. So there's a story in 2009. There was this boy who was 2 years old. He was at the Stanford hospital. And he had received part of a liver transplant a while earlier. And the transplant went well for a while, and then all of a sudden the boy became very, very ill. And the doctors suspected but didn't know why. They suspected it was because some of the bile ducts in his liver were clogged or otherwise not working. And so they thought, well, we would need an MRI. But to see the resolution that you need to notice the bile ducts in an MRI, you need a very high resolution image. Right? So when you run the numbers, you need an image that takes about 2 minutes to acquire. So keep in mind this boy is 2 years old. Telling him to sit still and not breathe for 2 minutes is not going to happen. So then you could think, well, what about anesthesia? You can put them under, you could stop the heart, you could stop the lungs from breathing, and even that's too long. The doctors are not willing to stop his breathing for 2 minutes. So what is one to do? So this is around the time that this mathematical theory called compressed sensing had just come into full bloom. And it was a way of capitalizing on the structure of natural images and medical images in a way that requires collecting less data. And so in this case, there's a chance that that less data could mean 40 seconds of a scan instead of 2 minutes of a scan. But it's a very challenging proposition because you collect less data. It's unclear whether you're going to have enough data to actually resolve what the image looks like. So let's see, let's compare an MRI image not using this method called compressed sensing to one using this method called compressed sensing. So this is an image without compressed sensing. It's zoomed in to the pancreas in this case. That's what the white arrow is pointing to. And as you can see, it's very grainy. But this is zoomed in. If this is the best you can get, we'll take it. If we could do better, we would prefer to do better. If you use the compressed sensing algorithm on the very same data, then you get this image, which is much better. And in particular, you can see this object. This line here is something called the pancreatic duct. And you can clearly see it here. And you really can't distinguish it from noise over there. So there's hope that this algorithm, this thing called compressed sensing, how to make do with less data, can actually really lead to better images. And back in the case of this 2-year-old boy at the Stanford hospital, the same authors of this study did the MRI. They looked into his liver, and they saw that in fact 2 bile ducts were clogged. And so an interventional radiologist went in and cleared out the ducts and literally saved this boy's life. So as you can tell, mathematics is very important. And to come back to where we began, let's remind ourselves of what we've learned. We've learned most movies are boring. Most images are boring. Most sound files are boring. Because they all sound like static and look like static and have no structure. But that is important because it means that if we know the structure of the images we want, we can store them in less data. And that allows us to communicate with the people we want to communicate with. It allows us to communicate with spacecraft at the edge of the solar system, and allows us to improve and save lives. All of these things have a future, and will get better in time. So if you want to be part of the future of these fields, one way of doing that is to choose to be good at mathematics. Thank you.